What if AI doesn't run on intelligence, but on electricity? Think of it this way. Electricity is to AI what oxygen is to a human. You can build the smartest brain in the world, but without oxygen, it shuts down in minutes. Right now, AI isn't running out of ideas, it's running out of power. Today, we're unpacking the hidden energy crisis, quietly reshaping the future of AI.
Welcome back to a new episode of Behind the Facts. I'm Maya.
And I'm Alex. In this episode, we're going to explore why AI's hunger for electricity is surging, why data centers are straining power grids, and what this means for energy markets, local communities, and the future of computing.
It really is the untold story of the last few years, isn't it? I mean, if you look at the headlines as we started prepping for this deep dive, everything has been focused on the compute race.
Oh, absolutely. It's been entirely about the chips. Who has the most advanced hardware? Who's building the biggest context window?
Right, we've been totally obsessing over the silicon, the actual brain cells of the operation.
Because that's the flashy part. That's the part that feels like sci-fi. But while we were all staring at the microchips, the ground kind of shifted beneath our feet. The bottleneck isn't just silicon anymore, it's shifting to electrons.
Yeah, it turns out the real limit of AI might not be how smart we can make the code or how small we can make the transistors. It's simply, can we plug the thing in without melting the wires?
Which sounds, I don't know, almost too mundane to be a crisis. Like we've had electricity for over a century. You'd think we'd have this figured out by now.
You would think, but when you look at the numbers coming out of the energy sector right now, the scale is, well, it's frankly staggering.
Let's ground this in some data, because I think you really need to visualize this to grasp the scale. In 2024, global data centers used about 415 terawatt-hours of electricity.
Which is a big number, sure.
It is. It's roughly 1.5% of the entire world's electricity supply.
Okay, 1.5%. That sounds absorbable, like it's significant but not world-ending.
Right, for now. But here is where the curve goes completely vertical. By 2030, that number is on track to more than double, hitting around 945 terawatt-hours.
Yeah.
And just to put that in perspective, that is roughly equivalent to the annual power consumption of the entire country of Japan.
Wait, Japan?
Yes, the whole country.
So in less than a decade, we are essentially needing to add a new G7 nations worth of electricity to the global grid just to keep the servers humming.
Exactly. And the scary part is the speed of this growth. Because standard servers, the boring ones that run your email or host your cloud photos.
The old reliable ones.
Yeah, their energy demand grows pretty slowly, maybe under 10% a year. But AI-accelerated servers, the ones doing the heavy thinking, their energy demand is growing by about 30% every single year.
So the stakes have completely changed. It's not just about who has the cleverest algorithm anymore. The race for AI dominance is turning into a logistics war. It's about who can secure enough cheap, reliable power to actually keep the lights on.
It's infrastructure. It's heavy industry.
Which leads to the obvious question, right? Where is all this energy actually going? Like, what is the AI doing that burns so much juice?
Well, we really need to break this down because there are two main phases to an AI's life, and they consume energy in very different ways. First, you have training.
Okay, the university phase.
That's a really good way to put it. This is when the AI is reading the internet, analyzing billions of parameters, learning the patterns. It's a massive one-off energy event.
Kind of like a rocket launch.
Exactly. Take GPT-3, for example. It has 175 billion parameters. Training that model just once consumed about 1,287 megawatt-hours.
1,287 megawatt-hours. Again, a huge number. Help us visualize that.
Think of it this way, that is equal to the electricity used by an average household for 100 years.
Wow. A century of power.
Burned through in just the few months it took to train one single model.
That's wild.
Or, if you want to think about scale, it's like the annual power use of over 100 homes, dedicated just for that one training run.
And that's just one model. Now imagine every tech company, Google, Meta, OpenAI, Anthropic, all doing these massive training runs simultaneously.
It's a huge spike. But training eventually ends. The model graduates from university.
Right. And that's where the potentially bigger problem comes in. It's called inference.
Inference is basically just the technical word for using it, right?
Exactly. Every time you open a chatbot and type a prompt like, write me a recipe for vegan lasagna, or summarize this PDF, that is inference. The AI is actively thinking, calculating probabilities, and generating an answer for you.
And how does that compare to, say, a regular Google search? Because I think we all just assume these digital things are free and easy.
It's not even close. A standard Google search is incredibly optimized. It uses a tiny amount of power. about 0.00003 watt-hours. It's basically negligible.
Okay.
But a ChatGPT-style query, that uses about 0.3 watt-hours.
So doing the math there.
It's roughly 1,000 times more energy intensive.
1,000 times.
Yes. One conversation with an AI burns the same juice as 1,000 web searches.
That really changes how you look at the phone in your hand.
It really does.
We're carrying around these tools thinking they're just magic software, but on the back end, every time we hit enter, we're triggering this massive energy draw.
And unlike training, which is a temporary spike, inference is the long, heavy baseline. It never shuts off. Millions of people, billions of queries, all day, every day. In fact, some projections suggest that by 2027, generative AI alone could consume as much electricity annually as a mid-sized country like the Netherlands.
The Netherlands.
Yeah.
Just for the chatbot.
Just for the chatbots.
It's incredible. And we can't just talk about the software here. We have to talk about the physical world.
Yeah.
Because all this energy usage requires buildings. It requires wires.
Right. This isn't happening in some fluffy cloud. It's happening in big concrete boxes on the ground. And those boxes are changing.
So let's talk about the infrastructure shift. Because we aren't building data centers the way we used to.
No, we're seeing a shift to what they call hyperscale campuses.
Sounds intimidating.
It is, kind of. These aren't your old school server rooms in the back of an office building. These are massive facilities requiring 100 to 500 megawatts of power.
500 megawatts.
That is comparable to the power needs of a small city, all focused on one single campus.
And inside those buildings, the density is skyrocketing.
That's the key. In the old days, a server rack, think of a metal cabinet full of electronics, about the size of a fridge, might draw 5 to 15 kilowatts.
Okay.
But these new AI GPU racks, they're drawing 40, 60, sometimes over 100 kilowatts per rack.
To make that relatable, 100 kilowatts is immense.
A single AI rack can consume the power of roughly 39 households. Just one cabinet.
Just one cabinet. And a room full of them.
Is basically a furnace.
Right, because computers get hot.
And AI computers get incredibly hot. Physics dictates that energy doesn't disappear, it transforms. In this case, it transforms into heat. Traditional air conditioning, just blowing cold air around the room, isn't cutting it anymore. It's too inefficient.
So what are they doing instead?
Liquid cooling. They are literally piking liquid around the chips to carry the heat away. It's like the radiator in your car, but for a supercomputer.
But that creates an environmental tension, doesn't it? Because cooling often requires water.
Massive amounts of it. Data centers evaporate water to cool down, and this is where geography becomes a real problem.
How so?
Well, a lot of these data centers are being built in places like the U.S., Southwest Arizona, Nevada, because land is cheap and there's lots of solar power.
But those are deserts.
Exactly.
So you have these data centers literally drinking up local water supplies just to keep the processors from melting, while the local communities are facing drought restrictions.
It's a cooling paradox. You need the power to run the chips, and then you need water and more power to get rid of the heat the chips create.
It really highlights how physical this digital revolution actually is. And that brings us to the consequences. Because you can't just plug a small city worth of demand into an existing grid without breaking something.
No, you can't, and we're already seeing the cracks form.
There's a crazy story out of Northern Virginia. Now, for anyone who doesn't know, Northern Virginia is basically the internet's engine room. It has the highest concentration of data centers in the world.
Data center alley, they call it.
Right. In 2024, there was a voltage fluctuation. Not a blackout, just a wobble. But because these AI centers are so massive, it nearly caused a cascade failure.
Which is the nightmare scenario for grid operator.
Roughly 60 data centers had to disconnect instantly, dropping 1,500 megawatts of load in a heartbeat just to save the grid from collapsing.
1,500 megawatts. That's like a nuclear reactor just vanishing from the grid in milliseconds.
Exactly.
That kind of volatility is terrifying. And it's not just the big events. Residents living near these clusters are reporting power quality issues.
What does that actually mean for them?
It means the hum and harmonic distortion from these massive facilities can actually mess with the electronics in nearby homes. Lights flickering, appliances acting up. It's highly intrusive.
And then there's the impact on our wallets. Because all this demand, someone has to pay for the grid upgrades.
The IMF actually did an analysis on this. They suggested that in the U.S., electricity prices could rise by around 8.6%, specifically due to this data center demand.
So essentially, everyday people are paying higher bills so that we can have faster chatbots.
In a way, yes. We're socializing the cost of the infrastructure, and that's creating real social friction. There's a new term popping up, energy gentrification.
Energy gentrification. That's a heavy term. Unpack that for me.
It's a concept scholars are using, particularly in places like Sweden or Ireland. The idea is that these big tech projects come in with global capital and essentially buy up the grid capacity. They claim the reliable power for digital infrastructure.
So what happens to the locals?
Well, regulators are forced to make tough choices. Do we prioritize the local bakery, the new housing development, or the hospital expansion? Or do we give the power to the massive server farm that promises tax revenue?
It's squeezing out the local economy.
Exactly. And people are fighting back. There are now over 140 activist groups in the U.S. alone fighting these projects. As impartial observers, we're just looking at the facts here, but these groups are genuinely angry about the noise, the water use, and the rising bills.
There's also an environmental irony here that we have to mention. AI companies love to talk about being green.
Oh, they love the net zero pledges.
Right. They want 100% renewable energy. But AI needs power. 2047.
And the wind doesn't always blow. The sun doesn't always shine.
So to meet that base load, the constant, uninterrupted power they need utilities are keeping fossil fuel plants open longer than planned.
It's happening right now. Coal and gas plants that were supposed to retire are being kept online just to feed the AI boom.
So in the short term, AI might actually be driving emissions up, not down.
It's a real risk. The demand is simply moving faster than the green energy can be built.
And this scramble for power, it isn't just happening in local neighborhoods, it's happening on a global stage. This is a geopolitical race now.
It really is. It seems like the very definition of a superpower is changing.
How do you mean?
It used to be that AI leadership was about having the best scientists or the most chips. Now, AI leadership equals energy leadership. You cannot have one without the other.
And we're seeing countries position themselves based entirely on their ability to provide electricity. There's this flight to cold happening.
The Nordic play.
Right. Countries like Norway, Sweden, Iceland, they're becoming the new hubs for AI.
It makes perfect sense if you think about the physics. They have cheap, renewable hydro and wind power, and crucially, they have cold air.
Nature's air conditioning.
Exactly. You can use the outside air to help cool the servers, which saves a ton of energy.
I saw that OpenAI has a project called Stargate Norway.
And Microsoft is investing heavily there too. It's almost a no-brainer. If you can move your training that massive energy-hungry spike we talked about earlier to a place where power is clean and cheap, you do it. You export the computation to where the energy is.
But not everyone has a Norway next door. What about the rest of the world?
Well, China is taking a different approach. They are leveraging everything nuclear, massive hydro, and yes, coal to build a grid that can support their AI ambitions. They view the grid as a strategic weapon.
Because if the grid fails, the AI fails.
Exactly. And then you have emerging markets, places in the Middle East or Southeast Asia who are saying, hey, we have energy resources, come build your data centers here.
Well, it's almost like a trade.
It is. They are trading their energy resources for a seat at the digital table. They're building power plants specifically to attract these tech giants. It's reshaping global alliances based on who can plug in the biggest computer.
It all sounds a bit precarious, honestly. We're straining grids, raising prices, keeping coal plants alive, and reshaping geopolitics. So is there a fix? Or are we just going to break the system?
Well, we're not going to just break the grid, at least hopefully not. The system is trying to adapt, and the biggest trend we're seeing is a pivot back to nuclear.
Nuclear is having a massive comeback in the tech world.
It's the renaissance of the atom, but specifically small modular reactors, or SMRs.
SMRs. So these aren't the giant cooling towers of the Simpsons era.
No, these are smaller, factory-built reactors. They're designed to be safer, faster to build, and modular, meaning you can chain them together as you need more power.
And the big tech companies are putting serious money into this.
Billions. Google, Amazon, they are partnering with nuclear companies because they need 247 carbon-free power. They know wind and solar alone can't cut it for the density they need.
They need baseload.
They need power that is always on, regardless of the weather.
And aren't these reactors still years away?
That's the catch. Most of these projects are targeting the 2030s, but the deals are being signed right now over $10 billion in commitments. It's a long-term bet that atoms will power the bits.
In the meantime, I've heard about this concept of grid independence.
This is fascinating. Some companies are realizing that the public grid is just too crowded and too slow, so they are essentially saying, fine, we'll do it ourselves. They are building data centers directly next to power plants. Imagine a server farm sitting right next to a nuclear plant or a massive wind farm, plugging directly into the source.
They don't even touch the public transmission lines.
Exactly. They bypass the whole bottleneck. It's efficient, sure, but it also raises questions about who gets access to the best power sources. If a tech giant buys the output of a nuclear plant, that power isn't going to the public grid anymore.
It's privatizing the power supply.
In a way, yes.
There is one paradox we should touch on, though. Hardware is getting more efficient, right? The chips are getting better at using less power per calculation.
They are. Every generation is more efficient than the last. But there is a trap.
There's always a trap.
It's called the rebound effect, or Jevons paradox.
Oh, I know this. It's like when cars became more fuel efficient, people just drove more, so we didn't actually save any gas overall.
Precisely. If AI gets cheaper and more energy efficient to run, we won't say, great, let's save electricity. We'll say, great, let's put AI in absolutely everything.
We'll use it for trivial things.
We'll use it to write our grocery lists, to generate memes, to talk to other AI agents, so the total energy consumption might actually go up even if the chips themselves get better.
That feels inevitable. But surely there's a bright side. Can AI help solve its own problem?
That's the hopeful note, and it is real. AI is incredibly good at optimization. We are starting to see AI being used to optimize the grid itself.
So using the AI to manage the electricity.
Exactly. Balancing loads, predicting spikes, integrating renewable sources, making the distribution of electricity smarter and more efficient than humans ever could on their own.
So the tool causing the stress might also be the tool that saves us.
It's a race. Can the AI optimize the grid faster than the AI breaks the grid?
That is the question of the decade.
It really is.
The real limit of AI isn't just smarter models. It's the energy required to sustain them.
Behind every breakthrough is a grid, a turbine, a cooling system quietly working at full capacity.
And when electricity becomes the bottleneck, intelligence itself becomes constrained.
Because in the end, the future of AI won't just be decided by algorithms, but by who can power them.
That's all for today's episode. If you enjoyed this one, take a second to like the video, subscribe to the channel, and share it with someone who'd enjoy it too.
We'll see you next time. And remember, while this infrastructure challenge is absolutely massive, human ingenuity and energy innovation are moving just as fast as the code.